So the correct IUPAC name for the following compound is, and if we look at our structural representation here, we're using a Newman projection to represent the three-dimensional structure of this molecule. So to get that IUPAC name, remember that's the systematic name. So that's the name that's going to describe this molecule and this molecule only. I think we probably want to take this Newman projection and get it into a bond line structure. So we usually have been doing with these is imagining that we're flipping it over. So when we do that, anything that's on this left-hand side ends up going into the plane. So when we use our dashes and wedges, that means it's going to be on that dash line. And anything that's sticking off to the other side is going to be out of the plane. So on a wedge. And so coming right down here, this carbon chain is going to be in the plane. So we're going to be able to represent that as a zigzag structure. So we want to count those carbon atoms, I think, first of all, to see how long this chain is. So we have, I'm just going to count from this first one, and then we'll see once we get it drawn if we're actually counting from the right direction for the name. So 1, 2, this back circle is carbon 3, 4, 5, and then one of these methyl groups would be 6. So we're going to draw a 6 carbon atom chain. And so this carbon 1 is, or what I've labeled as 1 so far. It may or may not be 1 when we get to the IUPAC name. We'll check that out after we've converted structures. So we've got 1 carbon atom sticking up. So this is carbon 2. So if you're looking at that carbon 2, it's got 2 hydrogens on it. So one's going into the plane, one's coming out of the plane. But where that's not a chiral center, I'm not going to bother drawing those in on dashes and wedges because it doesn't matter. The carbon behind it, carbon 3 is our chiral carbon because that's where we have the bond to this first group, an alcohol, a hydrogen, and that other chain. So that's our chiral center. So we see that the alcohol is pointing away. The hydrogen is sticking out. Right, so this is carbon 2, that's the front carbon of the Newman projection. This is carbon 3, that's the back carbon of the Newman projection. And we'll see if we keep this numbering system or not. So 2 and 3, we're just trying to get the structure drawn. And then we got a bond down to this chain. So we got a CH2, and then a CH, and that CH has a CH3 and another CH3. So we're just counting that 6 carbon atom chain. So 1, 2, 3, 4, 5, 6. Okay, and so I think 1, 2, 3, 1, 2, 3, 4. So we do want to keep that initial numbering system because that's going to put our alcohol, and alcohol is a priority functional group. That's why I chose that. It's going to give the alcohol the lowest possible number because once you have a functional group, that has to have the lowest possible number. So I'm not concerned about what number that methyl group is going to get. We're really concerned about that alcohol. So 1, 2, 3, 4, 6. Okay, so that means that our parent name here is 6 carbon atoms. And it's an alcohol, so you drop, so it would be hexane. You can see this in a couple of the options. So actually these bottom 2 are pentanes, so we can cross those off. So it's going to be one of these 2, and it's representing already that numbering system that we see. So we know that this is a 5-methyl. We see the methyl on carbon 5. And we could say 3-hexanol, or we could put the 3 in here. Let's be consistent. So hexane, 3-ol. So that tells you where the alcohol is located on that parent chain. All right. And so the next thing we want to do is we want to decide if it's R or S. And so we want to assign priorities to these groups that are attached to the chiral carbon. So you consider each atom and give priority to the one with the highest atomic number. So you have an oxygen, a hydrogen, a carbon, and a carbon. So that oxygen is the highest priority. Carbon is hydrogen is the lowest, right? Because that's the lowest atomic number that we have here, highest atomic number that we have. And then we have 2 carbon atoms. Well, 2 carbons, they're both carbon, they have the same atomic number. So then we need to consider what they are bound to. So carbon 2 here has bonds to carbon, carbon, and 2 hydrogens. Carbon 4, which is the other side of this chiral carbon, has bonds to carbon, carbon, and 2 hydrogens. So those are exactly the same as well. So we haven't found a point of difference yet. So now we need to move out to the next atoms. So now we're comparing 5 and 1. So carbon 5 has bonds to 1, 2, 3 carbon atoms and 1 hydrogen. and carbon 1 has a bond to 1 carbon and 3 hydrogens. So we have finally found a point of difference here, right? So we've listed them in decreasing atomic number, so carbon, carbon, hydrogen, carbon. So we see right away when we get to that difference. So that carbon has a higher priority than that hydrogen. So that means that this bond here, and we'll put it next to the bond. So we're saying this whole group attached to the chiral center. So that would be 2, and this would be 3. Okay. So there's one more thing that we want to recognize here. And that is that ideally our lowest priority group would be facing away from us. It would be on that dash line. So if you wanted to do some tricks to redraw it, you could. What I would do is I would recognize that the lowest priority is opposite where we want it to be, exactly opposite. So that tells me that if I'm looking at this molecule from this angle, what I see is going to be, the direction that I see is going to be opposite of what I would see if I could actually kind of put myself behind the molecule and look at it from the other way. So when your lowest priority group is opposite, what you can do is say, okay, let me draw my arc 1 to 2 to 3. This looks like it's R, but it's actually S. And that's because I'm standing from this side, I would see it clockwise, but if I could put myself behind the molecule where I actually need to be and look at it, I would see counterclockwise. So that is S. So that means that, here's our full name, that S5-methyl hexane 3-ol, which is option A.